Okay, thank you very much for introduction. And there is a typo in program page of the workshop site. It was written Osaka City University, and just this April, Osaka City University and Osaka Prefecture University merged into Osaka Metropolitan University. So please remember. Okay, so here is I talk about my talk is divided into three parts. First one is I call box ball game because you know that to study box ball system is a fun, and I want to call this game. To play it. So we are all box ball gamers. And in the section one, I want to mainly review about the, I first wrote a paper about box ball systems in the year of 2000. And since then, around maybe 5 years or 6 years around that time, I wrote several more papers. And the first part is about that. So people from integrable systems may already know about this, but please be, yeah, maybe there are, you have heard about that. And second part, it's more mathematical, and it's related to a recent work of mine. It's about crystal theory of quantum affine algebras. And if you have such crystal, you can construct a box ball system. And if time allows, I also want to talk about box ball system with boundary. There is some machinery to investigate such a system from quantum integrable systems. Okay, let's start. So from this page, the sheets are rather dirty, but first I want to prepare some sequence of sets. Index L goes positive integers. So there are infinitely many such sets. And we also prepare some map, which we call, in this talk, I only consider combinatorial R matrix, but there are also quantum R matrix, or there are several versions. So to distinguish, you have to put combinatorial. And for combinatorial R matrix, it's just a map from set BL of X. BL of X is just given by BL and another parameter X, and the elements are just given by X to the some integer and the element of BL. And we call this X spectral parameter. And this combinatorial R matrix is a map from a direct product of BLX times BM. L and M may be different. And we prepare different parameters. And we switch the order of the direct product. So graphically, you can write like this. So you have an element of BL of X, X to the D, B. And another element is from BM of Y. And it has Y to the some integer times C. C is an element of BM. And there are two lines, and you can think this as a kind of particle. Particle wants to go this way, and this particle wants to go this way. But somewhere there is a collision, and after collision, this particle B and C may change. But still, this should be an element of Bm. And this B prime is maybe different from B, but it's an element of Bl. And there are also some energy shift. So E have some is added to E plus H. So there is some additional energy here. And here you minus this energy. So that total is the same. And this H depends on B and C. And it takes values in integer. And we call this function energy function. So that's an R matrix, combinatorial R matrix. Okay, so we just have just to set B and BL and R matrix, and we need two assumptions to play box ball game. So first one is the Yang-Baxter equation. So you have three sets, BLX, BMY, BNZ, and you want to change it totally, change the order. So BN should go this here and here like this, but there are two ways to collide each particles, right? So first BL and BM collide, and next here you have collision, and this way collision. But the another way to collide, have collisions is this way, yeah. And what the Yang-Baxter equation tells is that the whatever the elements of these three sets have the same. So here is the same element here and here and here and here and here, corresponding place. And no matter how you have three sets elements to the same elements, then the output is the same. So this element and this element is the same, and this are same, and this and these are same. So that's what the Yang-Baxter equation says. So that's the first assumption, and we have second assumption. So I cannot see actually this flow because my computer is small. So second condition is vacuum property. And so there exists some distinguished element, zero, because this may change with L. So I denote this dependence to put this superscript. And there is some distinguished element, zero, such that sorry, these are mistakes. So zero times zero should just switch totally, okay? And just to change the order. And also the energy function is zero. So XD just goes to XD0. And YE just goes to, YE0 just goes to YE0. So we impose such a condition. And actually, H energy function, the additive constant is irrelevant. So we can always normalize. If there is some particular element, then we can take such normalization. So you can consider this as a normalization. Okay? And what is vacuum property? So we put, so here you put element 0 in B1 all the time. And from left side, we insert B, any element B. Then you have many R matrices here and here and here, and then you have the output of R matrix. And if you have this, then the R here, this is determined, right? And if you have some arbitrary element B, you have some other element than 0. But if this number of 0 are sufficiently large, then in the right end, you have always 0, 0, 0. And the output should be just 0 of error. So that's the second assumption. We call this vacuum property. So we only need these two assumptions. And then with this setup, so we have a sequence of sets BL and the R matrix. And we have two assumptions, Yang-Baxter equation and vacuum property. So with this setup, we can play the game. So take on elements of B1 in the upper places, right? Like this, right? All elements are from B1. And insert 0 of L from left side. Then again, you have many R matrices, and usually we have different output from B1 and different output from B2 and etc. And we continue the application of R matrices until we have something here. But if here in this sequence, if non-zero elements are enough, how do you say, very small compared to L. So L is very large, so that you have almost 0 here, and very relatively few B are non-zero. So if you consider such a situation, then you can expect that the output here is again 0 of L from vacuum property, because there are very many zeros here, around here. Okay. Then we can define a time evolution. So you have a sequence of elements of B1 here, and applying this operator, then you have a different sequence of elements of B1. So we define this map from this to this, just TL, because this depends on L. Okay, so that's a time evolution with respect to this index L. So I also need, just again, look at this picture. Sometimes I also need this spectral parameter, power of spectral parameter. So if we insert xd, x to the d from left side, and then you have something, some element, but the power becomes different. Power is different from this power, right? Minus h1, where hj is the energy function of this element and this element. And next, the energy of this element and this element, right? So there are mistakes here also. And eventually, you obtain the power. It becomes d minus h1 minus dot 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 hl. So I want to define this this integer except d to be el. But it depends on b1 to bl, right? This element is fixed, so this doesn't depend on this. So only depends on this upper sequences. So I want to define this value. Okay, now we can play the game. So let's consider the initial state. Okay, and we apply time evolution operator once. Then we obtain b1 to b1 upper 1, b2 upper 1, etc. And we continue these procedures. And after t steps, you have this. So we can consider this as a state at time t. So we can consider this as a discrete dynamical system because we have time evolution operator and we have only a discrete time, right? And also the site positions are also discretized. So we can consider this discrete dynamical system. But in Takahashi sensei's talk, they considered, they mentioned ultra discrete dynamical system. So this each B element of B1, and this is a discrete set. So in such a situation, we can consider ultra discrete dynamical system. And also this system depends also on L because we can change L. We can take arbitrary L. So this system depends on L. But if you can take L to the infinity as a canonical one, this setting L to the infinity has a meaning. So if you are worried about this dependence of L, then you can take L to the infinity as a canonical. So I explained that from the sequence of sets and R matrix, we can consider ultra discrete dynamical system, but I didn't explain why it is integrable. So let me explain that. So we have in the year, this is the first paper about mine about box-pose system. I wrote a paper with Fukuda and Yamada. And recently, I sometimes find a paper by Fukuda, Yamada, and Okado, but I haven't wrote such paper with the order of FYO. So if you take, so please correct. This is equal to this, right? Anyway, so we can actually show that we have infinitely many time evolutions, TL. And first, we apply, so P is a sequence of elements of B1, or P is a state, we can say state. And first apply TL and next TM. And we can apply first TM and next TL. And they are the output, the consequences are equal. So that's the first claim. And second claim is that the value of this EM is equal to after applying time evolution operator with any error. So first claim shows that each time evolution operator are commutative. And the second claim shows that the EM for any M is a conserved quantity under TL, but this L is also arbitrary. So how to prove this? So by this, if you have number 2, you can show that we have infinitely many conserved quantities. So maybe we can say it's integrable. So how to prove this? So to prove one, we draw such pictures. So P is a state, and we take the same state, and apply first TL. So you have this intermediate state. And next, we apply Tm. So inserting this 0 to m, we have the left-hand side of 1, right? So we apply first TL and Tm. So the outcome is the left-hand side of 1. And the right-hand side, we change the order. First, we apply Tm and TL. So this is the right-hand side. So how to prove this? So we only need the Yang-Baxter equation. So we can you see this? So first, we put this x here. And then from vacuum property, we have here 0, 0, and 0, 0, right? And first apply R from left side. Then you can, using Yang-Baxter equation in this part, you can move this line into the left of this intersection. And the result is this one. And the Yang-Baxter equation shows that this element and this element is the same, okay? So in this picture, it means that this element and this element is the same. So now you may understand how it goes. Next, we move this line to the left. Then you can show that this element and this element are the same. And after moving this through to the right end, you have this. And you also have this, because of this vacuum property, if this number of sites are sufficiently large, then you have 0, 0, and again, the vacuum property, you have 0, 0 in these places. So that's the proof of 1. And how to prove 2? It's quite, you can consider spectral parameter. So we consider with spectral parameter. So if we put x, b, these are the same from vacuum property. And as I explained, after coming to the right end, you obtain such energy. This was the definition of EL. So because this is the element of BL. So this was the definition of EL. And here again you have, but you consider this site. So this by definition it's EM of TLP, because we here you care about this sequence, right? So in this side, quite similarly, you have by definition this set and this. And from vacuum property, this power is equal to power here. And this power is equal to power here. So by Yang-Baxter equation, you now you can prove that this power is equal to this power because this comes here, right? So this is equal to this. So this shows this. So from Yang-Baxter equation, these two claims is easily proved. So now let's go back to the original box pole system by Takahashi Satsuma. In that case, we take BL to be, I don't want to explain much about quantum group or etc. But crystal theory now. But BL in this case is crystal of Earth symmetric tensor representation of UQSL2 hat. So this is the name of an algebra, and the SL2 hat is actually the simplest affine Lie algebra. And UQ means that it's a quantum group associated to this affine Lie algebra. Let me stop the explanation about this now. And as I said, it's not so difficult. It's just see, there are boxes, L boxes, and there are some zeros, and after that there are some ones. So the order of 0 and 1 is important. So going right, this integers should be non-decreasing, increasing or equal, right? So in representation theory or combinatorics, this object is called semi-standard tableau of shape L, L boxes from letters in 0 and 1. So if we set L equal 1, there are only two elements, and 0 and 1. And if you understand the representation theory, it's highest weight vector of UQSL2. And if we associate 0 to vacant box and 1 to the box with one ball, then you recover a usual box pole system. So is there any question so far? I go to section 2. So let's go to the, so I first explain affine Lie algebra, but and quantum group, etc. But I just show the whole table of affine Lie algebra here. I take from our paper in 2002. So I'm sorry that the figure is not so clear. I don't know why, but actually there are two lines, and there is an arrow, left arrow and right arrow. And for type AN1, it's just a single line. And for example, type BN1, these are single line, but the end line is double. And there are arrow rightward, like this. And for type well, so I'm sorry, but it's not so clear. But these are some data for each affine Lie algebra. So there are such kind of affine Lie algebra, different kind of affine Lie algebra. And from such data, we call such diagram Dinkin diagram. And if a Dinkin diagram is given, we can define affine Lie algebra by generators and relations. And relations are determined by such data in this graph. So these are affine Lie algebra, all affine Lie algebra. So and for each affine Lie algebra, we have quantum group. Actually, this G can be any Katsumudi, symmetrizable Katsumudi Lie algebra, but I don't. I only consider affine Lie algebra here, and we can consider quantum group associated to this Lie algebra. And a quantum group is a wide terminology, and there are, for example, Yang-Yangs or quantized coordinate ring or others. And if we to be more precise, we have to say it's a quantized enveloping algebra. Anyway, it's a quantum group associated to this affine Lie algebra. And we have some representation of each quantum group, quantum affine algebra. And they are indexed by two integers. One is K, I is a node, the set of nodes in Dinkin diagram, in the Dinkin diagram. And there are always zero. If
Hello,
it's an affine.
It's good to hear your cheery voice. And I wanted to thank you for the lunch. I hope you have a good afternoon, and I look forward to seeing you when you get home.
Yeah, is there a question? So K is so I is the set of nodes of the Dinkin diagram, and there is always zero if it's an affine Lie algebra. I'll show you. So this is the zero node, zero node. So affine Lie algebra have zero node always. So and except zero. K is not zero element of I, which is not zero. And L is any positive integer. And for such indices, we have a finite dimensional representation of this quantum group called Kirillov-Reshetikhin module. And I don't want to explain this much now. But the important point is that from such a module, we can we obtain crystal, okay? And we want to call taking this name, taking the name. I want to call this KR crystal. And what is known about these KR crystal? If G is non affine Lie algebra is non-exceptional. So maybe I should explain what is non-exceptional. So for A, B, C, D, the Dinkin diagram exists for any n, right? And here also A upper to D upper to there are Dinkin diagram for any n, but E upper 2, E upper 1, and E6, 7, 8, or F, or G, or E6 upper 2, or D4 upper 3. They don't have Dinkin diagrams for any lower index n. So in such a EFG or these things, restricted rank, we call rank, we call exceptional. And if you have for any n, we call it non-exceptional. Okay, so non-exceptional is A, B, C, D, or A upper 2, D upper 2. So if the G is non-exceptional, there exists such KR crystal. So Anne Schilling and myself showed that the existence, and with Ghislain Fourier, we explicitly investigated the combinatorial structure around 2008 or 9. And for G exceptional, so all cases not still open. I mean the existence of KR crystal, but we can say that for there exists K such that BKL, KR crystal BKL exists for any L. So for such K, we can play the game, box ball game. So how to play the game? So first fix K and set BL to be B upper KL. So fixing K, and we take this sequence of set. Then the R matrix corresponding to these two crystals exists, is known already. And they satisfy the assumptions. It's rather easy to show. Because it's rather representation theory explanation, but at this representation level, there exists quantum R matrix, and consider crystal is that we take the limit of Q equals 0 at the quantum R matrix. So quantum R matrix exists and satisfy Yang-Baxter equation. So combinatorial R matrix also exists. So we can play the game. So for example, if we take A type, higher rank n, so SL2 hat is SL2 hat is A11. So it's a higher rank generalization of box ball system. If we take K to be 1, then it becomes the box ball systems with balls n colors. So you have different color of balls. And if so far, we, for simplicity, I take these set to be B1. But actually, even if you take this side by side, for example, first side, BM1, BM2, etc., we can also play the similar game. And such a game corresponds to the box ball system with many balls at one side. So at one side, you can have balls more than one. So you have such a formulation also. Okay. So here I explained the time is pressing, but so important point to use to play box ball game with KR crystal is the following. For KR crystal, there is a very interesting bijection from such a sequence of crystals and rigged configuration. Rigged configuration, it's a new word, new terminology, and I don't want to define here, but I just show examples. And what kind of bijection? It's a bijection from states of states of boxable system. And if you consider some restriction, we call a highest weight state. And I don't, so it's a representation theoretical notion. And I don't want to explain here. But if we consider such set, then there is a bijection to rigged configuration. And more importantly, if you have a BBS state, if we are, so rigged configuration is something like sequence of Yang diagrams. These are Yang diagrams. And rigging, there are numbers at each row. There are numbers. And we call these numbers riggings. Okay, there are numbers. And there are rank, if it's rank n, we have n Yang diagrams. And after time evolution, the numbers in case, we consider, so first, if you remember, I first fixed k. So if k is fixed, then numbers in, so if k is 2, then numbers in kth diagram, so second diagram, increase by time evolution, increase in this rather simple way. So if L is infinity, sufficiently large, then it's just low length. So in some sense, it's the system is linearized by this bijection. So in the simplest example was considered by Kirillov, and Reshetikhin. And there are several steps, but in non-exceptional types, Schilling and Scrimshaw and also Sakamoto-san, we solved this we established this bijection in these years. So the existence of such bijection is very important in our KR crystals. Okay, so there are examples. Okay, I have 5 minutes. Okay, so this is type A, rank 3. And so there are 2 solitons, and these are time evolutions, t equals 0 to t equals 6, right?
Excuse me. May I ask a question?
Okay.
Could you go back to the previous slide, please? First of all, can you hear me? Do you hear me?
This one?
Yes. Okay, so I'm very interested. Please repeat again. Excuse the, I hope people are patient. This linearization is central to classical integral systems. And so as a way to solve the integrable systems. So can you, I'm having a little trouble following here, but can you go backwards? So can you take your P and then form the diagrams? You have that very simple transformation on the diagrams, and then you can go, back. Okay, how does the linearization work in the classical case? You take
classical case.
No, all the way back to KDV, for example. That's what I mean by classical case. In KDV,
I don't think this bijection exists in the classical.
No, I'm not asking for an exact bijection. I'm simply asking for kind of a spiritual connection. Spiritual, yes. So that's getting a little bit too touchy-feely. Let me ask this question again at the end of the talk. Okay. Can you? What does this have a slide number? Is there a number to the slide or something? We'll come back to this slide, please, later. Okay. Okay. Thank you.
Yeah, I remember. Okay, let me explain this example. So okay. So yeah, and the corresponding rigid configuration is this one. And you have two solitons here of length 5 and 3. And this length of solitons already appear here. So one row of length 5 and one row of length 3. This corresponds these two solitons. And the time system is linearized. And also we can, since we have the bijection also for type D, we can play with type D. And again, you have two solitons of length 5 and length 3. And the corresponding rigid configuration. So since this is rank 3, you have 3 Yang diagrams. And since this is rank 5, you have 5 diagrams. And again, in the first diagram, you have one soliton here, and you have the other soliton here, and the motion is linearized here. Right.
Sorry, so just a quick question. Are you changing conventions where the zeros, what were referred to as zeros before, now become ones? In the two previous
okay, yeah, right. You are exactly right. Sorry, I forgot to say that thing. So in this case, in the vacuum is 1. Sorry, vacuum is 1. So in my previous sheets, the vacuum was 0, but here 1 is vacuum. Okay, I just 1 minute. So I just show slides for section 3. So there is super analog, and it's rather recent work. And this is also very interesting. So that's a type A case, much color version. And if so we consider this place Lie algebra, and then the very interesting thing happens. If we only consider not super case, you have tableau with these numbers non-decreasing, so can be equal or increase. But if you consider super case, from upper letters, you cannot have the same numbers. So in some sense, these letters are kind of bosons, and these letters are fermions. So if you consider super case, you consider such a crystal with bosonic features and also fermionic features. So that I think this is very interesting. And the BBS was investigated by Ryan Solomon, and yeah, and very surprisingly, they are undergraduate students. I was very surprised. Anyway, so may I just show the slides, and let me stop. Okay, that's slides of the system with boundary, and we need a combinatorial K matrix, and we have reflection equation for a boundary. And we have some progress. There are some works in 2005, and very recently, we also constructed the new solutions. Okay, thank you very much. Okay,
okay, will this work now? So yeah, thank you very much. So could we, yes, the next slide? No. It was the one with the diagrams. That's yes. Okay, thank you. Okay, so please humor me and the audience humor me, because this is at a very simple level. When I said classical integrable systems, I simply I don't mean as compared to quantum. I simply mean go back to the quarter vector Friis equation. And
speaking, please.
Oh, my name is Ron Perline. Okay. Oh, so
it's not displayed.
Oh, I'm sorry. It's okay. Call me Perlin RK for the moment. Okay. So What do? You start off with your object, which is going to be moving, in which case it's a function. Here you have your P. Then you do the spectral transform and you get some new object. And then the evolution is very simple on the spectral side. And then you go backwards via the inverse spectral transform. So that's a way of solving the problem. Now, in the discussions up until that moment, when you were showing the slide, a lot of interesting information about these systems was discussed, and conserved quantities and commutativity in a certain sense. But that method or that way of understanding the transformation was not spelled out. Okay, so somebody who is naive about this but knows something about integrable systems is going to say, how does the spectral transform method correspond to this? So I guess I haven't exactly asked the question yet. So is it the case that you take your P and you associate it with these diagrams, and then the time one step is very simple? It's almost linearized. There's that minimum function.
You can go back.
And then you go back. Okay, so that's the method in this case, right? That's the method for solving this problem. Okay, all right, well, that's very interesting and makes a closer connection with the understanding that some amateurs like myself may have, the connection to integrable systems. Okay, thank you very much.
Well, one answer is that the liquid configuration has a very interesting property. So I define this time evolution by applying quantum R matrix, right? And in the liquid configuration side, the putting the R matrix, I mean the 0, 0 in my terminology, 0 upper L, putting 0 upper L in left side doesn't change this liquid configuration. So liquid configuration have a quantum R invariance. That's a theorem, and it's very difficult to prove combinatorially. And because of thanks to that property, you have such a very nice property, inverse scattering, right? Yeah, that's one answer from my. Probably Kuniba-san will talk on Thursday, and maybe I hope Kuniba-san will explain such sort of these topics around here more in detail.
Okay, thank you. And okay, Professor Harnard, please.
Yes, well, I'm also somebody who comes from a classical integrable systems background. And many things that you say sound familiar, but I'm not familiar with the box-ball system, so this is new. But there are several elements, and I'd just like to know, I guess like the previous person, I'd like to know if all of these elements, which are characteristic in the methods applied to integrable systems, whether continuous or discrete, whether these exist in these box-ball systems or not. So I already asked the first speaker if there was a lax system. I think that's more or less what the previous questioner was asking. If there is a lax linear system whose compatibility is equivalent to the dynamics, because that's really the starting point of all the classical integrable systems analyses. It's the inverse spectral method in one way or another. That's one question. I don't know the answer yet to that question. I think the answer is yes, but I don't see what the lax system is. I actually have about 2 or 3, but I'll try to say them very quickly. The second feature, which is very standard in integral systems, is the passage from continuous integrable systems like KdV, or more generally KP, to discrete systems. And then this is where I'm a little bit lost, to discrete systems, but then there was what the first speaker was referring to as ultra discretization or ultra local discretization. And that's, I think, when the zeros and the ones come in. That passage is also present in some very standard literature on classical integrable systems. And the way that there are two methods, but they are actually equivalent, two methods for discretizing such continuous systems. One is, well, you expand everything in a basis, let's say, of sure, you have a function in the continuous system, let's say the KDV system or the TODA system, and you expand in a basis of functions which are labeled by partitions, and those functions are typically sure functions or some kind of characters. And then you look at the so-called Hirota bilinear equations, which are equivalent to the dynamics. They're equivalent to the integrability of the Lax equations. You look at the bilinear relations and become purely algebraic. They become relations, quadratic relations between the coefficients in this expansion. Now, I don't know if any of this exists in these box-ball systems, but that's what my question is. I'm going to add one or two other things, and any of these things that appear, I would be very interested to hear about. The second method, which actually in a sense is equivalent, but it's a deep theorem that it's equivalent, is not to look at the coefficients in a standard expansion, let's say in a character basis, but to look at evaluations of the tau functions on a lattice. It's like Poincaré map evaluations. And this gives you also a lot of discrete variables, namely the evaluations on this lattice. Yeah. And they satisfy exactly the same quadratic relations that the coefficients do. And that is known as the addition theorem for hierarchies of integrable systems. I don't know if any of this means anything or is familiar to you, but it should be somehow present in these box-ball systems as well. And the very last question, so I'd like my question, there is a question here, is here's the list of objects that I'm wondering if they do make an appearance in the box-ball system. The first is the Lax representation. The second is the Hirota bilinear representation. The third is the Plücker representation as a lot of quadratic relations between coefficients. And those can, moreover, be expressed as lattice recursion relations. And one has such discrete systems as the cube recursions and the octahedron recursions, and all of these build up to give the same quadratic relations. So this list of things, and one last thing which I'd like to ask, I'm sorry to slip in 4 questions at the same time, but I'm just taking the opportunity. You and the previous 2 speakers always speak about solitons, and that's certainly a characteristic of classical integrable systems, the modern classical integrable systems. But they're not. But solitons are not the generic solutions of, let's say, KDV or hierarchies that include KDV. What is generic? The solitons are sort of singular limits of generic solutions, and the generic solutions are quasi-periodic, and they look like infinite trains of solitons. And that is really the sort of essence of the integrability in the classical sense. So I'd like to ask if that also, that 5th thing, the quasi-periodic solutions, which are not solitons, but they look like infinite trains of solitons, whether they are present in the box-ball systems also.
So there are too many questions that because of my weakness of my hearing of English, I cannot. So there were 4 questions, right?
There were 5. I will say the key words. I'll say the key words, and you can address whatever you're familiar.
Write an email summarizing the to me.
Well,
then
I could write it down, but I'm afraid that people will be gone by the time I write it down.
More easy to think, and also there are no time left, I think. So probably I think it's better to stop, right?
All right. This is the second or third time
how
that
about
I'm asking
Sasada-san?
these questions. But
yeah, if I were in Montreal, I will discuss for a long time. I can discuss for a long time, but yeah.
Okay, I'll put these into the
actually, they are very philosophical, and as far as I hear, some of the question may be answered, partly answered by Kuniva's talk, I think. Like
no, my questions are not at all philosophical. My questions are technical and precise.
Okay, so this is Ron Perline again. So Jean Renard was referring to what I call the kitchen sink of integrable systems because it has so many different aspects to it. And I guess what I was wondering, I think what you're presenting to the non-experts is the very starting point of the theory, and that maybe I, and other people want to know how many of those other points, that structural aspects of integrable systems, have been extended, and you just didn't have time to talk about it because there are a lot of interesting things that you have done that you didn't have time to talk about. So there can be many, many more. I guess we're expecting you to answer Jean Renard's questions in 5 minutes or less. And I'm joking. That's not going to happen. There are 100 papers that could be written at this point. Okay, so anyhow, thank you for the presentation.
Thank you. So there are many other people, no? You also, Han also want to ask something, but Han, it's okay? He already...
Yeah.
Okay, maybe later we can discuss. Okay.
Thank you. This is Robert Weston. Hello. I wanted to ask about the boundary case. So without boundaries, you characterize the ball and box game as having two conditions on the R matrix. So when you introduce a K matrix, you have one condition, which is the boundary Yang-Baxter equation. But are there any other conditions you need to impose to play the ball and box game?
Yeah, probably if you have the box system with boundary, you can double the horizontal line. So insert the vacuum from left, and there is the boundary, and this reflected by K matrix, and come to the, and probably you need to assume that this is another kind of vacuum, and it is also already known that the boundary matrix can go the same element, same set, or same set. I just call it empty set, empty, because I don't have any star here. And there is also a case that we have a kind of dual crystal, and there are two cases. And in either case, probably we need some. This should, if there are enough vacuum in this system state, then probably you need the vacuum if we go through all the through to this end. Then I think Baxter equation, reflection equation, and vacuum property for the previous case, and also this vacuum property will be enough, I suppose, to.
And does that ensure then solitonic behavior? So factorize.
Yeah, I think. I hope. I think so. Yeah.
Okay. Thank you.
Okay, one more question.
One more question.
Okay.
Vincent Pasquier, just because this would be interesting for physics, does the K matrix can change the number of balls? I mean, can it add balls or remove balls from the system?
I don't. So if we insert vacuum and the output becomes vacuum, then in some sense you have in representation theory. It's called weight preservation, and in such a case, the number of balls will be.
But at the boundary, I'm just thinking at the boundary.
Also at the boundary, right?
Also at the
in
boundary.
some sense, but you have to, in some sense, but you have to define the meaning of the sense correctly. But
Okay. So there are many nice, interesting points to discuss, I think. So, yeah, but at least about I think Voxball case for Lux or Hirota or some other properties will be actually discussed in this workshop, I believe. And so maybe, yeah, please enjoy this week's discussion. Okay, thank you very much, Professor Okado. So let's thank speaker again.